Guys, what's up? Today's demo is the boost converter, MOSFET based boost converter, and let me just show you. It's a basic one just for demonstrating, but let me just go into what all components I'm using here. So first of all, since a MOSFET is involved here, and the particular MOSFET here is, I don't think you can see it, always the clarity problem, but yeah, it's different from the last time. This is not the standard IRF Z4 4 and 55 volt MOSFET which I use. That's for low voltage ones, and since today I'm going to demonstrate a high voltage uh, here, this is a new MOSFET which I have got. This is the IRFP260N, which is a power MOSFET, and it has a VDS of 200 volts, which is it can have basically across its drain source terminals. So that's very nice. We can demonstrate much higher voltages than the low voltage one. So that's with the MOSFET. Second thing, what do I have here? Yeah, this is also another. This is a toroidal inductor, and it's a 330 microhenry one. Since these four components, let me just recap that these four components are absolutely necessary in any boost converter or buck converter or any kind of DC-DC converter. We always need an inductor, since the entire principle of this what do they say, this framework depends on the inductor's property of storing energy. So we need an inductor, definitely. We need a switching element. It may not necessary that it's a MOSFET, but generally it's a MOSFET. So yeah, a switching element, then a diode. Yes, we definitely need a diode, since the current should only flow in one direction. We do not want it to come back. So this is the particular diode here I've used is, again, not, it may look like a 407 rectifier diode, but it's not that. It's a high frequency diode, since we're going to be gating this MOSFET at a high frequency, switching frequency. This is a MER 460, they call it the ultra fast rectifier diode. So it's rated for high frequencies like this, and also 4 amps, which is plenty of current, and reverse voltage of 1 kilovolt if I'm not wrong. So yeah, that's good. And so that's the third element. We definitely need a diode. The last one is a capacitor, of course, to store the output voltage. And yes, the one which I've used here is a 10 microfarad 450 volt. So a lot, it's plenty, it's very high rated voltage capacitor. So we can definitely do this experiment without worrying about our capacitors blowing up. So this is a very nice capacitor. And yeah, those are the main elements. And now let's go into how the flow is. So first of all, uh, let me just show you the circuit diagram that will make it clear. Yeah, this is just a small circuit I made in multisim. So here we are going to be giving 12 volts is our input voltage, and that 12 volt, you can see I'm giving it here from my bench supply. It's set to 12 volts here. And we have the 330 microhenry inductor which I showed you, and the MOSFET which I also showed you, the diode, the output capacitor, and just a load resistor here, 10k. And yes, one more thing to mention, of course, the you must have seen this thing, the microcontroller. This is MSP 430, the Texas Instruments TI's MSP 430 family microcontroller. This is the MSP 430 G2553, and this is development, the that's the microcontroller, and this is a development board which is the MSP 430 G280 development board. So this is a nice handy board, low level microcontroller. By low level, I mean you program it in low level. And yeah, so that is going to be generating our square waves which we need for the gating of this to turn it on and off the MOSFET. And of course, this thing is a 3.3 volt, my what is that, CMOS technology, so 3.3 volts. And this thing can barely supply 6, I think the max current is 6 milliampere. So this thing definitely can't support this bulky MOSFET. So we need something in the middle. So what do we use? We use a gate driver, and there are these dedicated gate driver ICs, and that's exactly what I've used here. Let me just zoom in here. I think it's the same. Maybe you can see a little bit, I'm not very sure. Yeah, I don't think. Okay, so this is the international rectifier and now owned by Infineon. This is the IR2110 half bridge driver. So it can basically drive one high side and low side MOSFET in the bridge topology. But in this case, we just need to use one MOSFET. So we use it as the low side, just the low side. The high side we can leave those nodes not connected, no problem. We can just drive one MOSFET with this, but we definitely need a gate driver because this handles the higher voltage, which standard silicon MOSFETs need at least 10 volts to switch on fully. They start the VGS threshold. If you check the data sheet, it starts at 4 or so, and 5 volt also it will turn on. But the problem is it will be partially turned on, like in the linear region as they call it. So the resistance will be much more. The RDS on, as they call it, the on state resistance across the drain source terminal, that will be much higher. So there's going to be a lot of power dissipation if you don't provide enough gate source voltage. And yeah, that could be a problem. That's why it's always nice to give proper rated, and this rated at 10 volts as standard silicon, but here I'm going to be giving it the same 12 volts only directly, so that will be more than enough. The MOSFET will be fully on and we'll have the least resistance RDS on, so that is good. Yeah, so that is handled by the gate driver. And also the gate driver, yes, it will take the square waves from here and we give it to the gate driver, and it will basically output the same square wave, just amplified, if you so as to say. Like this will be a 3 volt 3.3 volt family, right? So it will be a 3.3 volt peak to peak 100 kilohertz square wave, and this will give you a 12 volt, which is your VCC, whatever you give here. 12 volt peak to peak 100 kilohertz square wave, so the same thing, just bigger, and it can supply more current. So that's what this gate driver's work is. Yeah, let me not dwell too much on that. So moving on, there is a series resistance here of 10 ohm to stop the ringing. Since it's a high frequency, you need a series resistance. 10 ohm is the standard value, and there is a 1k pull down there, so that when the square wave is low, when the input is low, we need to make sure the MOSFET is off, otherwise we get some floating state. So there's a pull down, and yeah, the rest of the connections are as per the circuit diagram, which I already showed here. So now I'll just a small peek at the code. This is the CCS Code Composer Studio for the MSP. It's a very small snippet, 20 line snippet to get the square wave. Just switched off the Mojadoc timer, setting bit 1.2. That's where I'm taking the pulses from, the purple wire, and that's where the timer output, the PWM, is going to come. And yeah, just setting up the timer here. I'm using the 12 megahertz clock. Inbuilt DCO generates it, the digitally controlled oscillator, and there's just some register level entries. And here, this is what sets the period, so it's the 100 kilohertz, and this is what sets the duty cycle. So currently I'm at 92% duty cycle. So if we just put it into the calculator, we're supposed at the input voltage of 12 volts at 92% duty cycle, we're supposed to get around 150 volts on the output, which is almost a 13.5 times the voltage. So this is a very big jump. From 12 volts directly you're generating that. So let's see if we get that on the output. So let me just switch on the setup now. I'll switch this on, the 12 volts supply, and now you can see actually across the resistance there's already 11.96, and that's not mysteriously appeared or anything. You just look at the circuit diagram. Currently I have not given the gating pulses. The gate is here. I have not yet given it to the MOSFET. That's why there's no switching happening as of now. But whatever supply voltage you give, the inductor, as its properties, it will act as a short circuit in steady state. So this is basically shorted here, and the diode is for getting forward biased. So basically you have your VCC across your load. So currently it's the VCC. Now as soon as I connect the gate, you'll be able to see the boosted voltage. So let me just connect this here and you'll be able to see it. Yes, and you can see immediately we're getting almost 160 volts there, which is a very impressive jump. And it looks like our boost converter almost over what did they say, went over our expectations. So we were supposed to get 150, we got 160 almost, which is must be, maybe if we tune the duty cycle a bit better and the tolerances, we take more of that into account, we will probably get the perfect one. But this clearly demonstrates that our uh, boost converter is working properly, the inductor is storing and discharging, the MOSFET is working as needed, and the capacitor is able to store the energy and later it's able to dissipate it through this resistor. So yeah, this uses the microcontroller, it uses power electronics, so embedded is involved, power is involved. So yeah, and of course analog circuitry. Only one thing to keep in mind here is the output resistance which you choose. Make sure the wattage is calculated and pre-calculated and put. So actually, if I touch this right now, it's a bit hot because it was 160 volts was across it, and it's a 10k resistance. So if we just do the I square R formula, P is equal to I square R, we were almost definitely dissipating more than 1 watt. So actually it wasn't that safe, but I didn't really have any other resistance lying around. So unless it's of course it's above the rated, so it will get hot. But as long as, that's why if you see I disconnected fast, if you just do it for a small time it's okay. But don't try and do like 1 kilovolt across this. If you try and make it 10 times or something of the rated, it's definitely going to go up in flames and your project is going to be destroyed. So yeah, always while doing this R&D, little we need to take care of the output here, since we are not really connecting. This entire setup was to just demonstrate how the boost converter works, so take care of the output load. But yeah, I think other than that everything works properly, so yeah, that's good. So yeah, that's it. I hope you liked it. Bye.